So we've been hearing a lot about precession and mythology related to it, and I think as several speakers mentioned, it's very deep in the mythological record with so many countries talking about it. And of course we're taught that it really wasn't discovered until Hipparchus, so they don't always call it by the name precession of the equinox, but sometimes they refer to it just as the movement of the heavens or the movement of the stars. And oftentimes they mention that it's caused by another star. And so we'll get into that a little bit. And the real scholar behind this work is our professors Giorgio de Santillana and Hertha von Deschen. And they wrote this brilliant book and talked about all these myths that relate to precession, but sort of lamented the fact that astronomers didn't really read a lot of mythology or pay much attention to it. Is that true, Jeff? See, there you go. And maybe they will after this conference a little bit, but there's a lot of mythology that relates to this, and we find it in the Norse myth about Fenja and Menja. And they're two maids, two tireless maids thought to be gods that never sleep, never tire. They go on endlessly turning the world axis in relation to the stars. And they're turning this sample. And in the higher ages, one period of time, the sample is turning out gold, and then it is turning out silver, and then it turns out salt, and then it just grinds out rock. So it's sort of similar to the world ages myth that we see. The Mithraic iconography also deals with this idea of somebody turning precession, but in this case, that somebody is Mithras, and he is the Mithras Sol Invictus, Mithras the unconquerable sun. And in our film, The Great Year, we introduced one of the professors at UCLA, whose name escapes me, but he'd mentioned that the Mithraic temples, which they found all over Europe, about 200 of them or so, have this iconography in it and talk about this sun outside the sun that seems to turn or control precession. And the reason this is so well preserved, an interesting side story, is that it was sort of the last pagan religion before the Christians came in, and they always built the temples underground, and they had stars on the ceiling. And when times were changing, coming into the Dark Ages, they just used these things as trash bins, and they filled up with debris and sort of preserved them for a few thousand years in some cases. And so we have very nice iconography about this fellow that turns this wheel of precession. You can just make out the zodiac there, and he's represented as a sun. You can see sort of an egg-shaped thing on his head. And in one part of the zodiac, light is going out, and they have a small a child there, and he'll typically be on one side. Sometimes they mix these up. Here he is over here, so darker age, and then this one signifies ascending or rising age. And again, the Sri Yuctus War, even though there's so much mythology about it, it was just kind of neat that he just kind of put it all in a nutshell. And he didn't take credit for it. He just said, hey, moons go around their planets, planets with their moons go around the sun, and the sun goes around some other star that produces the backward motion of the equinoctial point. He didn't even use the word precession. And he said that's all according to Oriental astronomy. And so we've been digging around and found out that there are indeed some old Oriental sources that talk about this. So if we were standing looking at space on the equinox every year, that's what the sky would be doing. It would just be moving, even though we're showing up at the same place every year. And that's the observable of precession, and it's thought, of course, to be due to the axis of the Earth wobbling. And it produces this thing that we've been talking about here, and the equinox simply is just an easy marker to mark the movement through the constellations. But as John Jenkins pointed out, some other cultures would use a solstice, as Maya culture did. So the current theory of precession is that the Earth wobbles like a top. And Copernicus said it wobbled, but he didn't really say why. Newton had come along 150 years later and said, well, gee, if it does wobble, it must be due to gravity. And sure enough, a lot of spacecraft, satellites, objects will wobble, and it's usually due to the fact that there's some torque put on them, or they're a little oblate like the Earth. The Earth's about 1/3 of 1% fatter around the center, and the Moon doesn't go exactly around the middle, it goes slightly off center. So it's a very logical assumption that this observable of the changing stars would be caused by the Moon yanking on. Is that mic cutting in and out? Maybe it's me. So we've been studying this for a few years, and with astrophysicists and mathematicians, and there's a few problems with it. One is the Maya are some of the best calendar makers in the world historically, and they base theirs on the Venus transits. And basing it on the Venus transits, you'd get off over a fairly short period of time because of precession, and yet the Mayan calendars seem to work just fine. And the most particular way that precession is tracked nowadays is that we have radio telescopes here on Earth. We look out towards a distant star or even quasar, which this is typically a point outside our own galaxy. They use something really far away because it eliminates parallax issues and things like that. And they can tell exactly how much the Earth has changed orientation during the year. And this is straight from the NASA VLBI website. Changes in the Earth's orientation in inertial space have two causes: gravitational force, the sun and moon, what we just talked about, and it's 99% the moon in the equations. And the redistribution of things on the Earth, which, creaking the Earth a little bit each way. And then NASA doesn't figure out new theories or anything. They turn it over to the geophysicists. The Earth changed by this amount. You tell us what the cause of that change is. And so they look typically just at geophysical causes. What might be wobbling the Earth a little bit. They really don't look at new theories or really, really old theories. But there's a few problems with the current theory, and one is we've noticed the Earth really doesn't wobble much relative to objects within the solar system. And NASA doesn't measure this way, and so it doesn't show up in any of the literature. And it's hard to measure relative to things in the solar system because everything's moving so much. But you can do a few math equations to figure out relative to the moon or relative to Venus. And we've done these in conjunction with some other people. And about 5 or 6 people independently around the world, an Italian scientist, a couple of Canadian scientists, an English scientists, have come up with the same thing. They just don't seem to see the Earth wobbling in relation to things locally versus relative to things outside the solar system. So it's kind of a paradox. If the Earth is wobbled by things close by us, mostly the moon, then why don't we see the Earth wobbling relative to something really close? Yet we see it wobbling a full 50 arc seconds relative to something far away? And so it makes us want to look at this idea that the ancients had. You know, maybe they knew something we didn't know. And if they're right, this mythology about a binary star, then that's, you know, where we're going to focus and have been focusing at the Binary Research Institute. So just a quick brief. A binary star system is just two stars gravitationally going around the same center of mass. They're gravitationally attracted to each other, and there's all sorts of variations of this, one star bigger or smaller than the other, which changes the dynamics of the orbit. And there's many multiple star systems where it's not just two, it's three or four or a gazillion in a globular cluster. So 100 years ago, these binaries were considered a rarity, and now we know that most stars in our galaxy actually have partners. Statistically, stars like to have a partner more than people do. It's that common out there. And you can see the figures. The 60 nearest stars, 60% are binary. The Chandra website on the web now says 80%, but I think that was before the recent discovery of more brown dwarfs, and they think a lot of them are just like to be alone. And so maybe that number comes down a little bit. So why wouldn't our sun have a partner? And if it did, then you get another possible way to create the precession observable. And that simply is, yeah, there's enough torque by the moon and local forces to kind of hold the axis just moving an arc second or two relative to those local forces, local objects, things within the solar system. But as the Earth goes around the sun once completely, you see different constellations. You see a precession through the zodiac, because of the sun's motion through space, not because the Earth is sitting there wobbling. So it's a model, and it's going to take a while to convince a lot of people of this thing, but we're just trying to figure out all the details and ramifications of it at this time, and then introduce it to anybody that'll listen. Jeff's one of the few that will actually listen. He's not made up his mind yet. Don't put any pressure on him. But he'll listen. We have about a half a dozen very good arguments for this, and one that's kind of simple to understand is the Perseids meteor shower argument. And as you probably know, as we talked about, the stars move across the heavens at the rate of about 1 degree every 72 years at the current rate. And that means that if you're on looking from the same day of the calendar each year, if you want to see the exact same stars overhead or at the sunrise or wherever, then that day is going to change every 72 years. You'll slip a day. So I've been attuned to the Perseids meteor shower because it happens to fall on my birthday, and so since I was a little kid, I've been getting up early to see that shower, or staying up late the night of the 11th. And it's beautiful, and it's caused by the Swift-Tuttle comet debris. And that comet debris think of it just as a big mark that goes through the ecliptic. The ecliptic is the Earth's path going around the sun. It's just the orbit path of the Earth going around the sun. And it goes counterclockwise like that if you're looking from the top, north. And so we see the meteor shower because we run into that comet debris, and we get these pretty lights. And it turns out that people have been watching this thing for thousands of years. It actually goes back, and they call it the Tears of St. Lawrence, because people have seen it right after St. Lawrence's feast day. And there's a bunch of calendar changes that happen. You know, they were really accurate up until right before the Dark Ages, and they got all goofed up. And we're kind of back on schedule now with the Gregorian calendar change in about 1580. And so if you just look at that 400 or 500 year period, and you look at the literature, well, the Perseids is happening at the same time, August 11th, 12th. And whereas it should be happening, if it's slipping one day every 72 years, it should now be happening on August 5th, 4th, 5th, something like that. So it's one possible proof that, gee, the Earth isn't wobbling relative to things close by, but it's still changing 50 arc seconds relative to something outside the solar system. Maybe that observable we call precession has a different cause. Is that pretty clear? Good. And it turns out if you use this way of looking at precession, you can answer some other solar system problems. One is the solar system formation theory, and that says it's a bunch of gas and dust that sort of was swirling around and slowly coagulated to form the sun and the planets. So everything in the solar system is supposed to have angular momentum, and the conservation of angular momentum is a pretty basic law of physics. You don't lose angular momentum real easy. And what angular momentum is just the angular momentum of something. So if I roll a marble across this stage and it weighs an ounce and it's going 20 miles an hour, it has an angular momentum of 20. If I roll a bowling ball across this stage and it weighs 200 ounces and it's going 20 miles an hour, it has an angular momentum of, what's that, 4,000, so a lot greater than the marble. Well, the sun's the biggest mass in our solar system by mountains. It has 99.99% of the mass, maybe not quite 99, but close to that. So it should have most of the angular momentum. Unfortunately, it doesn't, because we tend to use this static solar system model that says, the sun's not moving other than its spin there. We do, obviously astronomers acknowledge it's going around the galaxy, but that's generally not factored into this very much, or it is at a very low rate. And so all the planets have the right proportion of angular momentum, and we did this and then plugged it all in and said, well, what if the sun is in a binary orbit 24,000 years, and the low point was 1,500 years ago, and it made a few other assumptions, and this is what popped out as we sat there and watched it. Turns out the sun's angular momentum was there all the time. It's just a lot of it in its motion through space. Another funny thing going on with precession is the rate is increasing each year. And the sort of the old classical rate that some say they prefer is at 50 arc seconds a year. It takes you 25,920 years to complete a circle. That's why you often hear this 26,000 year number used for precession. But in reality, it's changing slightly each year because the precession rate is going up each year. And while we don't trust the historical records too much, we have really good records for the last 100 years. And these are by Simon Newcomb. And you can see the precession rate is going up at a pretty good clip there. They did change the methodology in the 80s. We're correcting it to better match some of the observables. But they were hoping, I think, to get rid of this constant a little bit, but it's still going up. And so the precession rate increases each year. And if you relate this to the changing ages, it might be an idea that we are in an ascending age. And the only good reason given now for why this is happening, when people started to notice it a few years ago, is, well, gee, the moon couldn't account for that because the moon's not changing gravity. We have reflectors on the moon. We can measure its distance. It's not getting any closer, so precession rate shouldn't be speeding up because of the moon. That's 99% of the force. So they started adding in asteroids and other things nearby, and finally somebody said, well, the Earth's core must be elliptical, and it's due to the elliptical core, and it's just so we'd kind of speed up and slow down because of this elliptical core. That might last a while because it's really tough to disprove, that what the core looks like. But we've looked at it a different way. We said, well, what if precession is just the observable of our solar system in this binary motion? What would this curve look like? You know, it would be following Kepler's third law. You'd have an increase in the speed of our sun relative to its binary, and a decrease. You know, an increase is when the gravitational bodies are close to each other, and then it goes slower as it's farther away, and then increases again. And so again, we plugged in our information, 24,000 years, blah, blah, blah. What would the curve look like 1,500 years after apoapsis, which is the farthest point apart of these two stars? And bingo, this is what popped out. It just fits right in there. And then we used Kepler's law to actually look at precession over the last 100 years and measure it, and found out that Kepler's laws were actually a factor of 10 more accurate than Simon Newcomb's method of calculating precession. So, sorry to get a little technical, but it looks like it works. So, and there's some other interesting anomalies, because if we're in a binary star system, it would probably affect other things that we're not quite aware of. And the Pioneer 10 and 11 data, we still don't know exactly what it means, but there's a few guys that have noticed that these are unpowered spaceships, just gravity, and they're not where they're supposed to be. It's indicating that there's an extra 200 Earth masses somewhere in the solar system, which sounds kind of strange, but gravity looks like it's got some anomaly going on there. You know, I acknowledge that gravity works really good locally, but as these things get farther out, it doesn't work too good. Some other data that came in this summer is the Voyager 2 data. Voyager 1 and 2 were sent out in 1977 to go take pictures. Voyager 1's whipped around Jupiter, got a big gravitational boost, and got out to the edge of the solar system in a hurry. Voyager 2 kind of took its time, gave us the first pictures of Uranus, Neptune, some of the big outer planets, Saturn. And so, just for simplicity's sake, let's say that Voyager 1 hit the edge of the solar system around 10 billion miles, and I don't remember the exact figure. They figured that Voyager 2 wouldn't get there for a couple more years. I think it was 2008 or 2009. And then this summer they announced that it's getting those readings. There's a Jeff knows this better than I do. I don't know if it's a bow shock or whatever, but they're near the edge of the solar wind there, where it's running into some resistance or slowing down. And it's happening about 8 billion miles. And so now some guys are saying, well, gee, maybe the heliosphere around the sun isn't a sphere after all. Maybe it's more bullet-shaped or comet-shaped. And so somebody said, you know, we must be running into a big dust cloud or gas cloud in that direction. And I'm just thinking, you know, maybe that's the direction of motion of the solar system. And that fits with some other data here we'll talk about in a little bit. So we're thinking we're in a binary system. We got to find this other star. I'm trying to meet as many people as I could, and so Jeff Patino and I, we went to the Keck telescope to spend the night with Jeff Marcy there. And about 2 o'clock in the morning, you start to talk about pretty loony things after a while. And we said, well, how much of the universe have we actually seen? And he says, okay, let me draw this out for you. I'm going to get a little professorial. And he says, well, we know that we haven't seen 70% of it because that's dark matter or dark energy, and all the galaxies are just zinging away from each other at high rates of speed. It takes a tremendous amount of energy to do that. So it's got to be a lot of dark energy. And most people agree with that. And I said, wow, then we don't know too much, but at least we know 30%. He says, well, not exactly, because we have something called dark matter. And we said, well, what's that? And we talked a lot about how galaxies are in these tight spirals, and yet when you look at them, there's just not enough mass there to hold them together. So there's got to be some bunch of dark matter we're not seeing. Otherwise, there'd be stars flying off the edge of these galaxies. The whole universe would be a little more homogeneous. And I said, wow, we only know then 5% of the universe. This was after we talked about WIMPs and machos and all types of different dark matter. And he said, well, not exactly. So most of that 5% is hiding behind gas or dust, or we think it's regular, ordinary stuff, but we really haven't seen it. And so I said, well, how much have we seen? And so look very carefully here. This is the entire visible universe. You ready? There it is. You know, Sergeant Schultz on Hogan's Hero, we know nothing, absolutely nothing. So when I talk to these astronomers, oh, it can't be, you know, it could be. So there are some very good astronomers starting to look for a companion star, and they've actually been doing it a long time, sort of under the radar, because it's not a really proper thing to do. And so Richard Muller and some have looked for brown dwarfs, Whitmire Matisse, University of Louisiana. There's a gal here, head of astronomy, Virginia Trimble, says she's getting in the game, and I think even Jeff has got a telescope coming on board that might be perfect for this sort of thing. So there's a bunch of dark star scenarios. You know, if we are going around a companion, we just can't imagine that we're going around a visible one, so it's got to be something close by, and therefore we haven't seen it yet. And the standard equations would say, you know, it's a lot closer than the nearest visible star. And so people are looking for things from brown dwarf to red dwarf to a black hole, and quickly eliminating the possibilities, by the way. And so that takes us to a whole other scenario. Maybe it's a visible star. And this is really sort of unheard of, because it's just not perceived that gravity is strong enough to really bind us to the nearest visible star, or perhaps we're not going fast enough to get around it in 24,000 years and back, and it's sort of a combination of the two. And but we are learning that, you know, there are some gravitational anomalies, and one theorist working on this is a fellow out of Israel. He's come up with something called MOND, which seems to work in a number of cases, modified Newtonian dynamics, and solving some problems. Another guy, Reg Cahill, out of Australia, has come up with some very interesting gravity problems. So a few people are saying maybe we could be going around a nearby star. And we have this, if we are going around a nearby star, then it's, the way gravity works, you know, whatever we're going around would make sort of a bigger dent in space. If something's going around us, then we're the bigger dent and it's the lighter mass. But because of the wording of some of the mythology, I'm actually looking for something bigger than our sun rather than smaller than our sun, which a brown dwarf is only about 8% of the sun's mass. And the biggest thing around in local space is the star Sirius. And that's handy because there's so much mythology about this star Sirius, the brightest star in the sky. But it's also problematic because there's a few stars closer to the sun, as you can see, Proxima Centauri and that system, Barnard's star, and a couple others. So if we are going around something like Sirius, you know, we need to really think through how gravity would work, and maybe it's a more complex system than we originally thought. But back to the mythology, there's a ton of myth and folklore about this particular star. And this is one I just learned fairly recently, that many of the old Shinto temples are aligned towards the star Sirius, and they actually call it our second sun. Sounds a lot like the Mithraic culture, which talked about this unconquerable sun. And the Egyptians, too, you know, they have a wonderful mythology about the higher age, the first time Zep Tepi And we don't understand half of their stuff. I took a class in hieroglyphics, and I've been, had a few hieroglyphic guys on retainer lately just to help me figure out some of this stuff. And recently I've got 4 different interpretations for Horus. But I'll give you the one that I like. And there's these 2 really important gods among many, but one of the most important is clearly Isis. And Isis represents the star Sirius. And she is often seen suckling Horus as a child, and then has some relationship with Horus as an adult. And this iconography is all over the place. I just got back from the Rosicrucian Museum up in San Jose, a great museum if you get a chance, and you'll see 50 things where Isis and Horus are getting together. And many scholars do say probably the number one reason or answer is that Horus is some kind of aspect of the sun. Nobody's quite sure. It might even be a concept of sun time or bigger sun time, something like that. But you can see him here with sort of the sun on his head, and he's often seen in some relationship where Isis is doing something. And this is the kind of relationship you'd expect if Isis, Sirius, and Horus, the sun, are gravitationally bound to each other. And there's other interesting mythology about a specific star out there. Some of you might have read Hamlet's Mill or Sitchin's work, where they talk about this crossing star, which Sitchin interprets as a planet. But this is the language out of the oldest epic in the world, the Epic of Gilgamesh, about 5,000 years ago, right after we started to need writing again. Wouldn't it be great if we were just in the Silver Age of just telepathically, and we'd all be at the beach right now? But he's talking that Nibiru, which most scholars I talk to, Spicer, Heiser, it's actually in the back of Hamlet's Mill, too. They refer to Sirius as Nibiru as Sirius, the star which in the skies is brilliant. Sirius is the most brilliant star in the sky if you look up at it. And it has it's crossing up there. And so this is how a binary system would work relative to our sun. It's kind of like we're both in the same reference frame. And think of it as a merry-go-round that, we're one sun, Sirius is 2 sun. We always maintain the same orientation to each other. And precession is merely all the other stars going around the outside. It's not the Earth wobbling, it's just, if we're on this merry-go-round together, we see our parents all going by at a certain rate because we're moving, not because the fixed stars are moving or not because the Earth itself is wobbling. And it turns out that a number of great astronomers have noticed this, and good scientists. Edmund Halley talked about this. And this is from a piece that comes from Jed Buchwald up at Caltech. And he's the professor of the history of science at Caltech. Pretty good guy, pretty good school. And formerly the professor of the history of science at MIT held Giorgio de Santillana's post. And notice this second sentence here. Sirius remains about the same distance from the equinoxes and so from the solstices, read the sun, throughout these many centuries despite precession. So it's a very curious motion for a star when it should be moving across, moving in relation to the equinoxes or in relation to the solstices 1 degree per 72 years. And if anybody gets a prize for this work, it's probably going to be this guy up in Canada, Karl-Heinz Hohmann. He and his son, Uwe Hohmann, have just done over 20 years of direct observations and come up with some interesting theories about Sirius. And what he's found is, well, first of all, I went up to Canada and went to their little setup there, and it's just a telescope in a basement that's it's all sandbagged and got dust on it because you can't touch it or you're going to ruin their transit readings. And so we're sitting there having tea about 4 in the afternoon. This is a couple of years ago. And he said, "Oh, Sirius is about to come by." And of course, it's just really the Earth turning to point it at Sirius. And so I go down there and I get to do this viewing on this day, and there's a crosshair there. Sirius is so bright you see it in the daytime. You know, it's like a second sun. And we're looking at it, and then the second count is coming off. He's got a clock right there with the crystal in the ground to keep it as accurate as possible. It's tuned in the atomic time at Fort Collins radio, and beep, 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 we're getting the seconds, and bingo, we mark it just to the second when the fat part goes across the cross line. It's good old-fashioned astronomy. And over time, he's noticed something interesting. The Earth doesn't appear to wobble in relation to the star Sirius. There's no precession in relation to this particular star, whereas there is precession in relation to other stars. So his idea is, you know, maybe gravity is hard to get going. You know, gravity falls off, therefore we can't be in a system with binary system with Sirius. That's what people say. But he's thinking gravity is like a big bowl, and if you can kind of just get it going, then it takes very little effort to keep it going. And he sees this very close companion of Sirius. It's called Sirius B. It's a dense white dwarf, goes around Sirius A in 50 years, and he thinks that's like the pendulum of the clock, and that sort of rocks our system. And you know, Pluto, I used to be able to say the one planet that's kind of out of alignment with the other planets is in perfect resonance with this AB ratio, and some of the other planets seem to have some sort of ratio. Sedna, which was just found recently by Mike Brown, I guess he's also a Caltech, and he is just went on and on in this cover story in Discover magazine this summer about how Sedna can't be there. This just doesn't work. This isn't supposed to happen, to have this great big elliptical orbit out there, but it happens to be 12,000 years. So again, it's in just such a nice resonance with the 24,000 year motion we're looking at. And that's the sort of phenomena you'd expect if this thing is real. And we keep exploring other ways to find confirming things. One thing I've been looking at lately is this Gravity Probe B. It's a very interesting satellite put up by Stanford and JPL. And they've got the best gyroscopes ever built by mankind, 4 of them. They say that if you spun them, they would spin for about 25,000 years before they stopped. You know, that's pretty cool. And it's got a telescope attached to one end of this, which is looking at a guide star outside the solar system. And I don't know how accurate the other side is, but they're keeping a polar orbit, and they're looking for general relativity, some geodetic effect, and frame dragging effect of the Earth, you know, just to prove whether Einstein's right about the Earth making a big dent in space-time. But they've really come out with some interesting little tidbits of information, too, that they're having this systematic problem that seems to mimic or cancel precession, which is kind of what we would expect if their gyroscopes aren't moving in relation to Earth, and yet they're showing precession in relation to the guide star. But it's hard for a guy like me to be able to talk to the right scientists, so maybe a friend of mine will help me get in there to talk to the right people. So after doing this work and kind of looking at both the ancient mythology and the modern science, it looks like maybe the ancients are right. And it wouldn't be the first time. You know, there was a system of the solar system that was popular in very ancient Greece. Aristarchus of Samos said that we were in a heliocentric system, meaning the sun's in the middle and the Earth goes around it. And Archimedes is believed to have taught this, and a couple other Greeks talked about it. And this was about 1,000 years exactly before the depths of the Dark Ages, according to the Vedic Hindu calculations. And then it just goes away in the Dark Ages, And then exactly 1,000 years after the Dark Ages, 1543, Copernicus says, you know what? This geocenter thing that the church was supporting and all these other people, it looks like really we need to go back to a heliocentric system. They found 5 books in Copernicus's possession. 3 of them were ancient Greek texts, you know. So it looks like maybe now we're ready for a new idea of the solar system, and that is perhaps it actually moves through space, and as it does so, it takes us in and out of a region of space that may have some effect on us somehow, and that's what the bulk of the talks tomorrow will be about. So thank you very much.